Welcome to this FEKO webinar. Dr. Jordi Soler is our Business Development Manager based in Spain, and he will be highlighting the new features in FEKO Suite 7.0, which is due to be released in May. Jordi will be launching a couple of polls during the presentation, which we hope you will participate in. He'll let you know when these happen. A recording of the presentation will also be available within 24 hours. You will receive a notification email providing a link to the presentation. We encourage you to post questions for Jordi throughout the presentation in the area provided on the right-hand side of your screen. You don't have to wait until the end of the presentation to post your question, but Jordi will probably only answer them at the end of the session if time allows. For further information on FEKO, please visit our website or contact your local distributor. You're also welcome to contact us via the email address that appears at the end of the presentation, webinars@emss.co.za. We'd like to ask you to complete the short survey at the end of the webinar, which will help us to improve our webinars as we go forward into the future. Over now to Jordi.
Okay. Today we are excited to present you the new features of this new FEKO release, which is FEKO 7.0, which we will be launching in the coming weeks. We have split the presentation into the following topics. Before introducing the major features in FEKO 7.0, I will give you a snapshot of how FEKO is positioned today in the market. Afterwards, I will present the two major features in this release, which are the finite difference time domain solver and the hybridization between our multi-level fast multipole method and the physical optic method. And finally, and before concluding the presentation, I will highlight some other very interesting features that you will be also able to enjoy in this release. If we briefly talk about industries, FEKO is widely and intensively used in many industries, being some of the most important ones: automotive, aerospace, defense, naval, communication, electronics, and healthcare. And FEKO is used in these industries for developing new products more and more in the early stages of the product design cycle, since companies want to reduce unnecessary prototyping costs, accelerate time to market, and detect and fix potential issues and problems in the first phases of the design cycle. Also, FEKO has become a virtual test platform for scenarios where measurements of the actual usage environment is challenging and costly. And last but not last, it is also worth mentioning the powerful program we have for the academia. Next, if we talk briefly about applications, some of the most well-known and key applications are related to antenna design, antenna placement, scattering analysis, cable coupling, electromagnetic compatibility, radon design, and RF design and safety, working from very low frequencies from Hertz up to very high frequencies like 100 gigahertz. At EMSS, we believe that no single method is capable of solving the whole spectrum of problems, which is why different methods are normally applied to specific applications. And in this slide here, you have different problems, different applications positioned in this map according to their electrical size and the complexity of the materials involved in these problems. And in FEKO, we have two sets of solvers. A first set of full wave methods, which are physically rigorous solutions, and a second set of asymptotic methods, which are high-frequency approximations, and where you can easily see that depending on the problem you want to solve, you have to select one method or the other. And also it's important to highlight that we have hybridized some of these methods in order to solve large and complex problems. Today we are introducing FDTD, and we have indicated this here with this blue rectangle for the analysis of problems involving complex materials like homogeneous dielectrics, and for problems which are not very big in terms of the electrical size. And on the other hand, we are introducing the hybridization between MLFMM and PO, and this is the reason why we have added here this green arrow. And this is, as you will see today, this is especially suitable for the analysis of very large structures. If we talk about the FTD solver and its related features, first we have one question. How has FEKO evolved with respect to frequency and time domain analysis? With Suite 6.1 and previous versions, a user had to request the required results on the frequency domain, could select a frequency domain solver in CAD-FEKO, which is our pre-processing environment for geometry modeling and where to set up the solution, and afterwards see the results also in the frequency domain in post-FEKO, which is our post-processing environment. Later, when we launched Suite 6.2 and also with Suite 6.3, the time domain analysis support was implemented in post-FEKO, replacing the old time FEKO component. Support for time domain modeling was included not using a time domain solver, as we are doing today with this new release, but with intelligent FFT and inverse fast Fourier transforms conversions that are hidden to the user. This allowed all methods such as cable coupling, PO, MLFMM, MOM, FEM, or the planar green function method to be really available. And to understand how this works today in FEKO and how it will also work with the new release, I will show and briefly explain to you now an example of the analysis of a lightning strike on an aircraft. We have here an aircraft with two antennas, one on its wing and a straight cable inside the airplane. We have a lightning strike entry and exit points as indicated in the figure, and we want to investigate which are the induced currents in the antenna ports and on the cable due to this lightning strike. To do so, we need to characterize the response of the platform from 1 kHz to 1 MHz using a specific pulse shape. Here you can see this double exponential pulse form. And we compute the currents within this frequency band, and then we just go to post-FEKO. In post-FEKO, we have a time analysis tab, which is indicated here in red. We then define and create a time signal with the required properties that you have in this dialog. And then FEKO calculates and gives us the induced currents at the antenna port, which is what you have in this other slide. You have the original poles in blue, and you have in green and red the currents versus time at the antenna ports which are loaded. We can also see the currents excited on the cable terminations versus time. In blue you have the excitation, in red the current at the cable end, and in green the current at the cable start. This helps now to explain how and what we have introduced and enabled in FDTD in this new release. In FEKO Suite 7.0, we are adding, as you can see now, the possibility to perform time domain analysis in a way that the user needs to make a request on the frequency domain, enable and launch the time domain solver get the results on the frequency domain, and with the possibility to show the results on the time domain via post-processing in FEKO. In future releases, as we are showing now, we will add time configurations so the user can make a time domain request in CAD-FEKO, select a frequency or a time domain solver, and get the time domain results directly in post-FEKO without requiring any post-processing. Also in future releases, users will also be able to represent native time results in frequency via post-processing in post-FEKO. Therefore, and is what we want to illustrate in this slide, FDTD can be used to obtain either frequency domain results or time domain results via post-processing. You know that in FEKO we have multiple configurations that provide users the option to obtain multiple solutions for a single method. In this, with FDTD, you also have to create a standard configuration for frequency domain analysis. Then FEKO automatically selects the suitable time signal, and the time interval can be either defined by the user or you can just FEKO decide for you. Regarding excitations, in this release with FDTD, we are supporting plane wave source, voltage source on wire ports, voltage source on edge ports, and also supporting loads on these ports. Going back to configurations, you will see that only one FDTD configuration is allowed at present. You can define multiple configurations, but they must be disabled. And regarding requests, you will be able to compute currents, near fields, far fields, including gain, directivity, and radar cross section, and the scattering parameter calculations. Regarding the workflow with FDTD, you will see that there are two workflows. First, one related to frequency domain results, where you have to create a standard configuration as it is done today in CAD-FEKO. And then to activate the FDTD, you just need to go to solver settings, you go to the FDTD tab, and you just have to select this checkbox in order to activate the FDTD solver. Regarding the workflow for time domain results, it's pretty similar. You have to create a standard configuration, activate the FDTD solver in the same manner as I have explained to you before, and then in post-FEKO you have to perform the time analysis. Also, it's worth mentioning that in CAD-FEKO you will be able to use the CEM validate tool to check that everything is set up correctly with FDTD, as it can be done with all the other methods. If we talk about the generation of the mesh, with FDTD we discretize the models into voxel elements, supporting non-uniform meshing for geometry and mesh parts, this being aligned to key points and boundaries. Also, if we talk about advanced mesh settings, you will see that there are options related to the growth rate, the aspect ratio, and also the handling of small geometry features. And with respect to the size of the meshes, as with our other methods, you will see that there are 4 options. You can just select the standard mesh, fine, coarse, or customized one. And for the standard, fine, and coarse meshes, the automatic settings take into account the simulation frequency, the material properties, and the time signals. There are some extensions on the voxel mesh. You will see that you can control the display of the voxel faces, the volume, and wire segments. You can also define cut planes through voxel elements. You will have the options of a monochrome display. And in post-FEKO, as with our other methods, we have enabled the voxels in the Find Elements tool, where you can find, display, or annotate a specific voxel element. If we talk about boundary conditions, you will see that we have two boundary conditions. The first one is an open boundary, which is based on a convolutional perfectly matched layer, CPML. And the second one is a perfect electrically conducting PEC boundary. And of course, the distance of the boundary can be automatically determined or can be defined by the user. And here you can see an image from FEKO, where you have in green the open boundaries and in orange the PEC boundary. We have prepared a set of examples to show you a cross-validation of FDTD with some of our other methods, and also to show you the advantages of FDTD in terms of memory requirements and runtimes. The first example is related to a PEC sphere, and we want to compute the bistatic radar cross-section of this sphere at 300 MHz. Now, if you look at the chart at the bottom, you can see in green the RCS computed with method of moments, and in violet you have the same but computed with FDTD, and you can see that there is a nice agreement between the two methods. One of the things that also would like to highlight here is that creating the geometry, meshing it, configuring the properties, running the simulation, and also displaying the results is something that we have worked to have this done very easily in FEKO, as you will see when we launch the release and you can play with it. The second example we have prepared is also related to a sphere, but in this case it's a PEC sphere coated with a dielectric coating with a permittivity of 4.0. We also want to compute the radar cross-section, and in this graph you have three curves of the RCS, in red for FDTD, in blue for method of moments, and in green for MLEMM. And you can also see that for this problem there is a nice agreement despite of this null that we are seeing here for FDTD. Another example that we have prepared today for you is the time analysis of the effect of an incident plane wave on an obstacle on a PEC Cube. And in the next slide we are showing you the results of the compute electric near field versus X for different frequencies. Here you can see the results at 500 MHz comparing FDTD in blue and method of moments in orange, and you can see that there is a very nice agreement between the two methods, and this agreement can also be found at 0.75 GHz and also at 1 GHz. The next example is the study of the propagation of an electromagnetic pulse, EMP, in a scenario where making field measurements is challenging. This was relevant for a client of ours regarding the shielding of electronic equipment. And here you can see that we have a two-story building and we want to investigate the transient fields caused by these electromagnetic pulse. The building structure is simulated with FDTD using a typical pulse, and the results are cross-validated with the frequency domain method of moments at the specific frequencies within the spectrum of the pulse. Here we show you a first slide with some results where you have the electric near field we are comparing FDTD with method of moments at 2 different positions, and you can see that also the agreement is very nice. This can also be seen through the near field distributions. On the first row, you have the magnetic field computed with method of moments and with FDTD on the right-hand side. And on the row below, you have the same, but for the electrical field. And again, if you compare these distributions, you can see that there is an excellent agreement between them. Finally, in terms of computational requirements, here you have a table where we show methods where you have MLEMM, in this case using the surface equivalent principle, and FDTD. You have the memory that was required to solve this problem, you have the runtime, and you have here information about the machines we used to solve the problem. You can see that by using FDTD, we can reduce the memory requirement by a factor of 9 and runtime by a factor of 7. And here I would like to point out a couple of aspects. The first one is that by having different methods, and in this case method of moments and FDTD, we can cross-validate the results in a situation where it is difficult to get measurements. And on the other hand, we are showing that, and for this particular example, FDTD has relevant advantages in front of method of moments if we look at the memory and runtime. And the last example we have prepared for you today is related to human phantom modeling. While method of moments offers a superior computational efficiency for design working with homogeneous phantoms, up to now we had finite element methods to model inhomogeneous dielectric bodies. Also in 2005 we hybridized method of moments with FEM, and in 2012 MLFMM with FEM to take profit from both methods in the same problem. And now with FEKO Suite 7.0 we can also solve inhomogeneous dielectric with FDTD as well as with MLEMM, which again offers a clear advantage for the user to cross-validate simulated results for applications where obtaining measurements is complex and costly. Here you have an example using an anatomical head model with 8 tissues simulated at 300 MHz. You have the electrical near field, also the SIR here on the row above for the hybrid MLEMM and FEM method, and on the row below for FDTD. You can easily see that the results are agree very well. And here we would also like to point out that we are now extending the phantom model database thanks to our collaboration with Simpleware and the human body models. And on June the 18th, we have our next webinar, which touch on healthcare applications, and where you will be able to know more about this. These are the slides that cover what we wanted to explain you today about FDTD. And now, as Fiona has said at the beginning of this webinar, I would like to launch a small poll. So I will just now launch the first question. Okay, one moment. Okay, which is the question is: do you currently use an FDTD solver? You will now see the poll, and you should, if you want, you should answer yes or no. We give you about half a minute to think and just and to be able to reply if you want. Okay, thank you. Now I will close this poll and we will launch a new one with another question, which is if you answered no to the first question, we would like to know if you do have a need for an FDTD solver. Now I will be launching this poll. Okay, then again, I would appreciate if you can answer this if you want, and we give you about half a minute to reply. Okay, thank you very much for your answers. I will now close the poll. Okay, and now we will continue with the second major feature we are introducing in this new release, which is the iterative hybrid multi-level fast multiple method together with physical optics. In 1992, we introduced the hybridization of MLEMM with PO. In 2004, MLFMM, a full-wave method especially suitable for the analysis of radiation and scattering problems involving electrically large structures. And now with FEKO Suite 7.0, we are introducing the hybridization of MLFMM with PO to solve extremely large structures, and where MLFMM is used to model the complex part of the structure, the fine details and the sources, and the high-frequency physical optics approximation is used to model the smoothly varying parts. Also in FEKO, we have the large element physical optics method. This is an alternative set of basis functions which allows us to have mesh sizes of multiple wavelengths. This leads to dramatic computational cost savings relative to the standard PO. And as you will see in the next slides, we have also implemented the hybridization of MLFMM with large element PO. We will explain this new iterative method through an example of a horn antenna and a reflector. We are modeling the horn antenna with MLFMM, and here JMOM stands for the currents on the FLMMM region, and the reflector is modeled with PO, and here JPO stands for the currents on the PO region. The iterative process to where is based this iterative algorithm works as follows. First, we initialize the PO current to 0. We compute the MLEMM current using MLFMM, and afterwards we use the scattered magnetic field caused by the MLEMM currents to compute the PO currents. Then the scattered field caused by the PO currents radiates back into the MLEMM region, and we modify the right-hand side vector of the iterative solution. With this new right-hand side vector, the process from step 2 is repeated until convergence is reached. How you will need to activate this new solver? You should go to FEKO, you should go to the solver settings dialog, and as you can see here in this image below, you should go to the MLFMM tab, just select solve model with MLFMM, And next, go to the high frequency tab, and just here select couple, PO, and MLFMM. Regarding this example that we're showing now to you, we have a waveguide horn with 7,800 unknowns for the MLFMM, and for the PO we have a reflector that has a diameter of 36 lambdas. Now we are showing here the computed gain for this antenna. You have in blue the results for MLFMM, and in green the results for the new iterative solver. You can see that there is a very nice agreement between the two methods, and only on these angles here there is a slight deviation. But now what happens if we do not take the coupling between the methods into account? To illustrate this, in the next slide we show you again the gain. In blue for MLFMM, and in red we have plotted here the results using the MLEMM and physical optics method, but being decoupled. And you can easily see that with all these differences across all the different angles, that this is a case where the coupling between the two methods is something that you need to take into account. In terms of computational requirements, here we have added a table where you have the number of unknowns for the MLFMM, the number of unknowns for the PO in the case of the iterative solver, and also the peak memory and runtimes. You can easily see that with the new iterative solver we require 16 times less memory, and it is about 40% faster for this relative small problem. And if we wanted to analyze the same problem but using the coupled version of the method of moments and physical optics methods, it could take us days to solve that. Another important characteristic for this iterative solver is convergence, and here you have the formula just to compute the JMOM current, and in this table below you have the error for different iterations, iteration number 2 and 3, because as you will be able to see, this new method converges fast and with just a few number of iterations. The second example we have prepared for you is a monopole antenna on a circular ground plane, where we are modeling the antenna and the area around the antenna with MLFMM, and also the dielectric sphere with MLFMM, and the rest of the structure with physical optics. In this table here you can see the evolution of the error for the different iterations, and if we look at some results, you have here a graph showing the gain of the antenna. In blue you have the results for using the method of moments coupled with physical optics. In green you have the results for the new method, and you can easily see that there is an excellent agreement between these two methods. And we also have wanted to include the results for the decoupled version of the method of moments and physical optics method, because here you can see that again this is a case where it is important to take this coupling between methods into account. And the last example we have today for you is related to a Cassegrain horn antenna, where the main reflector has a diameter of 63 lambdas, and where we are modeling the horn and the sub-reflector with MLFMM, and the main reflector with physical optics. Now, in this next slide, you can see the computed gain. And in this case, you have the results in blue using MLFMM. In red, you have the results for the hybridized version of MLFMM with PO. And also here, we have included the results for the hybridized method that we have also introduced in this version, which is MLFMM with large element PO. You can see that the results for the three methods are almost identical, and only with the MLFMM large element PO there are some slight variations at these angles. And what happens if we just now look at the computational requirements? Here we have added a table where you have runtime in hours and peak memory in gigabytes for the standard MLFMM, and for MLFMM with PO, and also for MLFMM with large element PO. You can see that if we compare the two first, MLFMM PO is a bit slower than the standard MLFMM, but in terms of memory there is a significant reduction if you use the new iterative solver. And also for this example, I think it's a nice case where you can see that by using the MLFMM hybridized with large element PO, runtime is much lower than with the other two methods, and also the memory you need to run this problem is much smaller. And the other thing that I would like to point out here is that if you would like to use the fully coupled method of moments with PO here, you would need 98 gigabytes of memory, which is, I think, and this shows the big difference between the new methods and the method just using method moments and PO. And in summary, for this iterative MLFMM-PO, we would like to say that this iterative technique yields a significant reduction in memory. And if we compare to the full MLFMM method, we have seen with the waveguide, horn, and reflector that it uses 16 times less memory, being 40% faster. It converges fast and with just a fewer number of iterations. And with the Cassegrain horn example, we have also seen that we require 10 times less memory, even though it's a bit slower. And for the MLFMM large element PO, we use almost 30 times less memory and being 6 times faster. And this is all we wanted to show you today about this iterative MLFMM-PO solver. And now, as we have done with the FDTD solver, we will launch another poll consisting of 2 questions. I will now launch the poll for the first question, where we ask you if you want to answer which hybrid solvers do you use. Again, we would, if you want to answer, we give you about half a minute to answer. Just thanks again for taking the time to answer this question. We'll give you a bit more time. Okay, thank you very much. Now I will close this poll and I will launch the final poll where you will see the following question. Do you think that the new MLFMM-PO hybrid will prove to be, and you have to select very useful, not sure, not useful. Okay, here it is. And again, if you can, please, if you want to answer, we give you about half a minute to answer. Okay, thank you very much again. Now I will close the poll. And we can continue with the final part of the presentation, where I will be explaining you some other minor features, but that I think will be very useful for you. The first one is related to importing PCB file formats. We have received some requests from clients to have the possibility to import into FEKO the designs of PCB using Gerber format, ODB++, and 3DI format. And this is what you will be able to use in FEKO 7.0. And for example, here in this slide you can see the PCB of a mobile phone customer sent to us in ODB++ format. We imported that into FEKO. We added the antenna you can see here, and here you can see the computed surface currents on the PCB and on the antenna. Also, regarding graphical interface changes, we have made a significant number of extensions and bug fixes. You may recall that in our previous release we introduced the possibility to work with high-order basis functions with curvilinear elements. And now if you want to display the instantaneous currents, you will be able to use multiple arrows per curvilinear triangle. Regarding options in FEKO for exporting, you will now be able to export information about the residuum for iterative solvers, and also information about the mesh to the out file. With respect to the characteristic mode analysis, which is a feature which is very useful to get insights about the intrinsic radiation properties of structures for antenna design and placement. Now you can use the characteristic mode index as an independent axis. And regarding our application programming interface, our API, now via the scripting interface, you will be able to access the characteristic mode results. You will also be able to control the stored result entities, and also we have extended the matrix and complex matrix objects. Now if we talk about other kernel improvements, we also have done a significant number of extensions and bug fixes. We also support more near and far field import file formats for easier data exchange with Sigrity, CST, Satimo, and Microwave Vision Group. And here I would like to point out that this is especially interesting that now you will be able to use data of measurements done, for example, with a Satimo chamber, with a Satimo Star Lab, for example, import that measurements into FEKO and use that as a source in FEKO, which I'm sure will be interesting for some of you. You will also be able to, for each S-parameter solution request, to have it written to a separate file. With non-relating transmission lines, you will also now be able to specify the background medium or the velocity of propagation. And regarding finite arrays, we have in FEKO a very nice tool to analyze large finite arrays based on the domain green function method. And now you will be able to also use waveguide ports when using this feature. And finally, here we would like to highlight that we have increased the accuracy of the green functions calculation for distances larger than 10 lambdas. If we talk about licensing and pricing, we have several options. We have a FEKO Lite version, which is a free version, but a limited one, but it is good to get to know the basics. You need to register for free if it is used for more than 30 days. Our standard and complete evaluation license is available for 45 days and can be downloaded from our website. And you can either purchase or rent a FEKO license. We have 4 categories: the bronze, silver, gold, and platinum categories. And what I would like to point out here is that one of the main characteristics of FEKO is that you have in one package you have a complete set of solvers for one price. And this will continue to be the same with the new 3 solvers that we are introducing today. And to conclude this presentation today, I would like to highlight again that we are introducing a time domain solver based on FDTD, where you will be able to do frequency domain analysis, including scattering parameter calculations, where we have been talking about the Voxel measure and the boundary conditions. And on the other hand, we have been presenting the new hybridization of MLFMM with physical optics and large element physical optics, which is an acceleration of the hybrid MLEMM-PO solver. We have the iterative technique for the calculation of the coupling between regions, as we have shown to you. And also, the large element PO formulation includes bidirectional coupling. You will be able to access to a lot of information by reading the release notes when we launch the new release. And of course, as usual, we will include all the information on our website, and also you will be able to download the new version from our website. And that said, I would like to thank you very much for your time and attention today. I will now check if there are any questions from your side, but you can also contact us using this email address, webinars@emss.co.ca, or contact your local distributor. Please remember that we have our next webinar on June the 18th. It is about electromagnetic field consideration in healthcare. You have here the link where you can register, and also keep in mind that all the webinars are available on our website on the link you have here. And then just thank you very much, and I will look now if there are any questions from your side. Okay, I'm reading one question here. Okay, there is one participant asking whether FDTD is supporting GPU, and the answer is yes. We are supporting GPU acceleration for FDTD and for frequency domain simulations. And also there is another question here. Yes, and the answer is yes. You will be able to access the different methods also in the FEKO Lite version. Okay.
Thanks, Jordy, for that informative presentation. We hope that you enjoyed it, and I'm sure everyone's looking forward to the launch of 7.0 later this in May. If anyone has any more questions, we still have a little bit of time over. It doesn't seem to be that we have any questions. So we'd like to thank you for joining us, and we look forward to hearing you on the 18th of June for our next webinar. Thank you very much.